Okay, folks, in order to distinguish families that arise from functional groups, you must begin seeing like an alchemist. What does that actually mean? It just means you must know how to first recognize and then draw carbon skeleton. So carbon skeleton is going to be probably the way that you're going to see most of our compounds in organic chemistry because it allows us to keep all the information about the actual organic compound without having to write so much. Okay, so you'll see the skeletal structures that just show carbon atom and carbon-carbon bonds as line. Okay, and then of course, if it's attached to any other heteroatom or any kind of functional group, you'll see their attachments as well. What attachments you won't see are the carbon-hydrogen attachments. Okay, folks? So it's all about making sure you recognize things. So sometimes that also includes recognizing the Lewis structure and the condensed structure. Let's start with the molecular formula. Here we have C3H8. That means you have 3 carbons and H8. So we're taking molecular formula and we're using Lewis theory, just like in 101, and creating a Lewis structure. But because we have multiple carbons and they're all the same electronegativity, we need to make sure that they're all going to go in the middle. So for the Lewis structure, we have 3 carbons in the middle, and then we have it flush with all the hydrogen. Again, you can call this a hydrocarbon because it's only carbon and hydrogen here. So again, you want to just remember from 101, the least electronegative is in the middle, and if there's multiples like we see here, they're all in the middle. So the Lewis structure, sometimes called the complete structure, sometimes called the expanded structure, is going to give you all bonds that you see attached to carbon, all of them, okay? And so, yes, that could be great, but think about it. If you had a carbon that's like 12, if you had a structure, a organic compound that's like 12 carbons, for example, you're going to be drawing a lot. And so the Lewis structure is not going to be your best friend when it comes to that. So in organic chemistry, we go a little bit further and we say, okay, instead of having Lewis structure, let's go ahead and create our condensed structure. And it's better because, again, it reduces the amount of drawing by eliminating the lines between carbon and hydrogen. Sometimes you will see condensed structures look like this. Okay, and that's just showing you that this bond is showing the bond between carbon and carbon. So yes, condensed structure can either take all of the lines away, like you see here, or all the bonds to carbon, or it can show carbon-carbon bonds. Okay, folks? So just keep that in mind. Another thing about the condensed structure that you will see is that sometimes it also shows repeated units. So say we had more carbon, it wasn't just C3 here. We had more carbon. You can put actually CH3, and then in parentheses, all right, say you had like 5 CH2s, you can put CH2 there. So technically we have 5, 6, 7 carbons in this structure. But if you have repeated units, instead of writing CH2, CH2, CH2 for the condensed structure, you can simply put in parentheses and have a superscript of the amount of those repeated portions. Okay, again, carbon is modular, so it can have all these little pieces coming together, which is pretty cool. All right. You also can see the condensed structure that includes, like, say, carbon attachments to heteroatoms, like nitrogen, oxygen, etc. We'll see that as well. So condensed structure can show you a lot, and no matter what, you should be able to go between the condensed structure to Lewis structure and condensed structure to a skeletal structure. Now, skeletal structure is a big unit, what we like to see. It's easier to draw. It's all going to be lines based on those carbon-carbon bonds, okay? Now, skeletal structure, it simplifies everything. But if we have something like an oxygen group attached here or a nitrogen group, we definitely write out the actual functional groups or heteroatoms for it, okay? Hydrogens are not drawn, and then you see carbons is represented at the endpoints of a line. So let me just erase this here and show you. This will be a carbon atom, this will be a carbon atom, this will be a carbon atom. I kind of just wrote little mini carbon mans just to show you that, hey, these are carbon atoms. We don't show the connection between the hydrogens here because, again, that is going to be excess writing that we mainly see in the Lewis structure. Also, we are assuming that each carbon has an octet. That's another reason why we're like, oh, we don't need to look at the hydrogen atoms there because we know that carbon has an octet. And so we just fill up however many hydrogen atoms are needed. If it makes a double bond or triple bond, of course, we fill up less hydrogen atoms that are needed. Now, let's talk about lone pairs. So with the skeletal structure, sometimes when you have heteroatoms attached, you actually will not see the lone pairs written. So if I have a nitrogen, we know that nitrogen likes to make 3 bonds and have a lone pair. Sometimes you'll see it written, and sometimes you won't. Okay, so here, like, I have a skeletal structure that's attached to a nitrogen, so we know that we can write the lone pairs. Or if it's not written, you should already assume that you know that there's lone pairs there because of how nitrogen exists. Okay, same thing with oxygen. You should assume oxygen is going to have 2 lone pair groups if it's making 2 bonds. But really, the lone pairs are optional. Something that's not optional when you're talking about skeletal structure, definitely not optional, is going to be formal charge. So formal charge, let's go ahead and rewrite that. Formal charge is going to equal to your valence electrons minus lone pairs plus 1/2 of your bonding pairs, or whatever way that you learned it, okay? So valence electrons minus lone pairs plus 1/2 of your bonding pairs. So again, if I have my NH2 here, if I want to get the actual valence or formal charge of nitrogen, I'll say, okay, 5 valence electrons minus lone pairs is going to be 2, plus 1/2 of what it's bonding to. So that's going to be 1/2 of 3. Okay? And of course, not 1/2 of 3, 1/2 of 6. Sorry. 1/2 of 6, because each bond is going to represent the sharing of 2 electrons, right? So this is going to be 5 minus 2 plus 3, which is going to be 5 minus 5, which equals 0. So the formal charge here is 0. That's why it's like you don't have to write it. But anytime you have a charge that's actually attached, so let's go ahead and do this. Say you have an oxygen that has a minus charge. You must keep the formal charge that's going to be attached with any heteroatom. Okay, so just keep that in mind as far as, let's give a couple more examples. All right, so let's just say we have this skeletal structure here, and we're going to have oxygen, no, it's not true. We're going to have NH3, but of course we don't have, instead of lone pairs, we're going to be plus here. Now you have to ask yourself, well, can I get rid of that plus? The answer will be no. You have to make sure you can recognize these carbon skeletons in all these different forms and be able to go back and forth between them, but also stop yourself and say, wait a minute, do I need to have lone pairs here? You don't have to, unless the question specifically said it. For example, do I need to have a charge? Yes. So let's go ahead and get the formal charge of this nitrogen here. So again, we have 5 valence electrons minus lone pairs. We don't have any, plus 1/2 of 8. Okay, so 5 minus 4 again equals to plus 1. So that's how we got the plus 1 charge here. See those charges? Go ahead and keep them. All right. We also know that we're looking at another flashcard moment, folks. So on the front of the flashcard, you can write carbon skeletons. On the back, you can write some examples of Lewis structures, condensed, and skeletal structure. Let's go through a couple of examples just to get us started.